Thank you, Paul. My name is Leon Reznik, and I'm a professor of computer science at the Rochester Institute of Technology, New York. First off, let me thank Paula, Hua, Jamie, and all others for organizing this great workshop. And I hope I didn't forget to mention lunches, did I? And please consider this presentation as a small sign of our gratitude. So what I'm going to do here, I will talk about our work, and we tried different industrial systems to see what level of cognition they demonstrate, and then think about what we can do to improve it. And first off, of course, I'm not pretending that we have done a comprehensive analysis or full review of all those systems. We just tried to use them for our purposes. The first thing, what we call link. Nowadays, machine learning applications are commonly executed as a cloud service, and to be able to do it, they need some data, which is commonly collected and communicated through some kind of network cyber infrastructure. So we call it machine learning integrated with network cyber infrastructure systems, and those systems again include the whole line from data generation devices through networking to machine learning applications. Again, we want to see how this stuff works together. Looks like, okay. And there are quite a few examples of all those symbols, and I'm quite sure you have seen a lot of those examples around. For example, just walking around Phoenix, I saw over a couple of days quite a few Waymos which are traveling alone, and that's probably the good example which we want to work with. Again, I have to admit we didn't work with real cars. We don't have Google or Waymo capacity. We work just with some models. Everything is working, but there is a small problem. When data is good, the system is working good and demonstrates a pretty nice performance. However, the problem is that when the quality of data which is submitted to machine learning application goes down because of major reasons like technological problems, problems with sensors, and some malicious attempts which do want to change data and decrease the quality of this data too, we may run into problems. And that's where some big bad things might happen. And again, we might run into safety problems, we might run into some crashes, and security of end users. So what can we do to do that? Probably we can try to develop some methods, techniques, models, which will improve robustness of the end applications. And actually, a lot of people are doing it. And over these couple of days, we have heard quite a few different techniques and methods and models which try just to improve it. What we are trying to do, we are trying actually to consider this robustness from the point of ability of machine learning system to maintain acceptable performance under various conditions. And we were trying to address a few research questions which can help us to solve this problem. Problem number one, is this a real problem for industrial applications? Are industrial systems robust enough nowadays? Problem number 2, how to evaluate and predict machine learning systems' performance in practice. And problem number 3, how maybe we can improve it. So again, people have been trying to address this problem, but again, the biggest problem, in my opinion, is that we have a lot of people working on it, but everyone is an expert in their own field. So there are quite a few techniques and solutions which could be called data-centric. And again, we can try to improve data quality by doing certain data processing, pre-processing, cleaning, wrangling, working with data distributions. And again, quite a few examples have been demonstrated over these couple of days. Another possible technique is model-centric. And again, quite a few examples have been demonstrated. We can talk about transfer learning, adversarial learning, machine learning parameter tuning, and some other techniques. Someone is working basically with the sensors, with data sources, trying to improve the quality of data coming from sensors. Someone is working on machine learning applications, trying to improve the performance of those models. And there are a lot of people in networking who are trying to improve communications. What, again, is missing some kind of integration. We want actually to put connections between those things and consider probably getting some feedback from machine learning applications to networking and maybe to data sources. So that's why we are moving up to some kind of higher level and trying to solve this problem. And again, our ideas is to move to lean cyber infrastructure, which is available, to Mlink, because again, the problem is that there are quite a few multiple pieces of knowledge which are used separately to solve some kind of independent problems. What we are trying to do, we are trying probably to demonstrate how those knowledge pieces could be integrated to come up with some kind of knowledge which could be applicable on different parts together. And again, we can see a common pipeline of data coming from sensors to networking through networks to machine learning applications. And if we look at it, again, data comes from data sources to machine learning applications. And if we are satisfied with machine learning application performance, nothing needs to be done, everything is fine. If the performance drops below acceptable level by specification for this particular application, then what we want to do, we want to adjust some of those parts or all of those parts together. And again, we are trying to get back not to a particular case, but to probably to quite a few of them together. To do that, we have to understand the current performance. And again, quite a few techniques have been already discussed, and those techniques might come through some kind of experimental approach. We can try to evaluate performance by executing machine learning application on some kind of target set, or we can use some kind of substitutes, because if, for example, certain industrial system produce some kind of evaluation parameters like confidence level, which could be used to substitute the performance. And again, quite a few techniques have been reported today about some kind of deriving the performance estimate from other inputs. Or we can try again to predict the performance at the next step, again based on machine learning and models and techniques themselves, based on some kind of using technological metrics, because again, a lot of technological metrics are used. There are some metrological characteristics which are used to evaluate the quality of data coming from sensors. There are a lot of metrics which are called network quality of service, which are used in communication. But again, the problem is how to use those techniques together. Again, we are trying to address this problem and get machine learning performance results on pre-processing components. Then we can get data quality evaluation coming from the sensors. Then see how this data quality changes over data communication through the network, and then how the change of data quality might influence the performance of the end application system. And based on that, we are trying to develop some feedback to tell what needs to be changed or adjusted. So what can we change? We can change data sources. If a lot of sensors are available, we can try to change data sources and replace one with another, trying to get a better data quality at the end. We can change original data quality coming from sensors, again, by using different data cleaning or data adjustment procedures. We can adjust networking and communication structures and procedures. We can change channels, routes, protocols, and again, and other things. We can change machine learning models and techniques, and we can change the learning process. So a lot of options are available. And again, those solutions do exist, but the problem is how to choose the right one. And again, we are considering this nice scenario with autonomous driving, and we use this scenario on the models. And again, the problem might come if the second car is not able to see the traffic sign because of some obstacle. It might be using some kind of communication through the first car or from some kind of roadside sensors which are available. But again, if communication, for example, is not good, then quality of data drops, and the traffic sign which is communicated to the second car might not be recognizable. Or it could be the result of some kind of attack too. That's the basic practical problem which we considered. And our goal is to develop methods and tools aimed at ensuring machine learning application performance, even under varying conditions of the data quality which is submitted to the machine learning end system. Now, that's actually our goal. Now, what we did, we tried to first to submit data of varying data quality to a number of industrial systems, and to try to address those two problems. Systems which we considered: Amazon Recognition, Google Vision. We have not got publication yet for Google Vision. Two commercial systems, and other systems are open source: Yola, ResNet, VGG, efficient net, inception, and those systems we used for image and video recognition. We tried some more, like IBM Deep Speech, and that system used for a voice transcription system. And we tried a couple of more which we used for sound recognition. So then we tried to simulate different networking conditions. So we tried to see what might happen over communication. And to do our experiments here, we use Powder platform, which is run by University of Utah and developed as a big NSF and industrial project. So we could simulate different networking communication conditions and see what happens with the data over communication, and then to submit this data to the end application. And here is the list of practical cases which we considered. The first one, again, traffic sign images classification. And we use just subset of ImageNet for picking up just traffic signs. Then we tried to substitute this ImageNet set with our own data because we wanted to put specific bad conditions like snowfall, rain, with traffic signs. So we took images under bad conditions and added them up. Then medical image classification, and again we just use images which were available online. Sound classification, voice recognition, and object detection. Basically we used images which were available online. And with video files, we again use BDD 11.0K image video set, but we added some videos of our own too. Again, we're trying to add some data of rather poor quality. So we started with simulating different deteriorating conditions which should decrease the image and video quality. So what we tried first, playing with color and with contrast level. And we found that actually industrial systems are pretty good at it. So you can replace color images with gray images, and the recognition is still very high. Then we started adding noise. And again, with low noise, practically again, recognition is very good. So we found that unless you add noise up to the level that actually it's much higher than the signal. So we found that actually industrial systems are pretty good at adjusting to standard bad conditions. And the standard bad conditions, again, I'm calling something like, again, noise level, something which could be probably fixed by filtration. And again, probably they either have this inability embedded into the system, or they have been trained on the images which contain those bad conditions. So then, again, we decided, okay, everything is so good, so what could happen? The bad thing which could happen is data loss. So we started simulating various communication conditions which resulted in packet loss and resulting in data loss of data submitted to the end application. And here the results started deteriorating. So, and this is an example again of packet loss for image and for VGG inception, efficient net for a few open source systems. And you see then when we have, when we have data loss a few percent, recognition performance goes down very significantly. So it means that with images, even whatever 5% of data loss results in practically not applicability of those end systems. It means that actually probably current AI systems, at least image and video systems, working with images at distance, are good enough at, again, filtering data, but don't have embedded data restoration procedures. Or at least at certain acceptable level. We tried to do data restorations ourselves, and we applied quite simple interpolation procedures. It does help. So probably, again, it might be fixed. Here are some more examples. Here are medical images. And surprisingly enough, again, we work with the images which we found online. Again, we tried to substitute images from some other sources, but then we decided that we'd better not to do it because of some ownership problems. So these are results with images which are available online. And you see that even in the initial images, we have something like 90% performance, which is not really very high for images. But then it goes down pretty soon. So again, even if we lose whatever 2-5% of data, probably we cannot accept it. Here is the system which recognized sounds like gunshot, fireworks, and surprisingly, the results here are better. Maybe, again, sound signals are rather redundant, so even significant drop of the data didn't result in very significant recognition performance. Voice recognition and transcription, about the same like with images. So just a few percent, and we have very significant drop in performance. And this is videos, and we tried again Amazon recognition, and we tried open source system, and surprisingly, okay, we expected with videos we can accept pretty high level of data loss. It didn't work this way. Just a little of data loss results in going down pretty soon in performance evaluation. So it looks like video systems are not good, are not cognitive enough. So that's the real situation. And based on this data, probably we can try to predict performance of various end systems. But then we decided to think about what we can do about it and what we can try to improve. And here are a few options which we considered. Again, as I said at the beginning, we can try to change data sources. We can try to adjust networking communications, and we can start working with learning. So let me start with first two, which are simpler ones. So again, Sensor could fail, sensor could be covered with dirt, happens, unfortunately, pretty regular. So it will result in some data loss, it might result in some violation of data integrity. Even without any intended malicious actions. But of course, bad guys are always there, so we can have some kind of malicious attacks too. With networking communication, again, network quality of service could go down, which will result again in some kind of packet losses and data losses. And again, we might have not improper data processing and pre-process procedures, and we can lose some data quality here too. So again, we try to find some kind of generic parameter, generic concept, which could let us to go through the whole pipeline. And we decided to concentrate on data quality because, again, we can see how to evaluate the data quality at the beginning and then proceed with trying to see how data quality changes through the whole pipeline. Data quality is some kind of concept which might include various metrics, and we have to probably try to integrate those metrics together in order to come up with some kind of integral indicators to be used for evaluating final data quality and its influence on the performance. So again, we have been looking through the whole thing, and the first thing which we decided to do to address data quality at the data source. To do that, we designed a framework which selects a combination of data sources which is able to deliver a specified data quality to the end system application. We have been solving a few problems like metrics integration, data integration, knowledge utilization in this framework design. And we tried it on the application with sensors embedded in mobile devices, like your smartphones. It was an SF project, so we tried to build up some kind of first database with characteristics of a lot of sensors, and we found mainly online on manuals characteristics of a few thousand sensors which are used to put into smartphones and other mobile devices, and we created the database, and then we use this database to evaluate the data quality of those sensors, and then to produce the integral indicator to give it to the user. And we developed a genetic algorithm-based approach which helps us to solve this problem in more or less real time. Again, time is important because we consider security as a part of data quality. So with attacks coming, we have to change probably data sources. If a particular sensor is under the attack, we want to change it pretty soon. Next thing which we investigated was data communication. So different protocols could be used in data communications. Some of those protocols allow data loss. For example, you know that UDP-based protocols which allow data loss in order to increase the speed of data communication. If you use UDP and your data loss exceeds certain level which results in end system application performance drop, probably you have to change protocols. And this is just one example. So based on that, we develop some kind of rule-based systems with rules telling how to adjust hyperparameters of networking communication. Again, for example, if performance drops but delay time is acceptable, we can change from UDP-based protocol to TCP-based protocol, which would decrease the data loss but increase communication time. And again, to formulate these rules, we need some knowledge of communication. And probably the most interesting part, what so far we considered system adjustment over deployment. In this part, we are trying to think about how to adjust the system over learning. And again, we considered two major approaches. One, and again, they have been discussed here. One approach is transfer learning, and another approach is federated learning. And again, we try to see if federated learning is worse or better, maybe, than transfer learning. So we found out that, again, the best performance the system can achieve if I feed the system with the quality of data which it was trained on. So, for example, if the system is fed with the data which includes 5% data loss, I would better use the system which was trained on this quality of data. If it was trained on, say, on perfect data, the performance will drop. If it trained on 10% quality of data, the performance will drop too. So that's an acceptable result. So how to make it happen in real systems? Because how do I know which data quality the system was trained on? Again, probably we have to train we have to use different units which are trained on a particular data. In this case, learning is conducted on this particular unit, and then we can aggregate the models which have been trained on specific data. That's the ability which federated learning gives us. So again, we tried it, and federated learning demonstrated pretty good results. However, with federated learning, there are certain problems. And one vulnerability which we found out particularly bad is that conventional federated learning sends back a global model to all data sources, which works fine if all those sources are good. However, if we do have one or a few data sources which is already controlled by adversary, who may submit intentionally bad information, what's happening with conventional federated learning is that we are actually sending back this good data, good model to bad guys. And again, that needs to be prevented, but to do that, we need to identify those bad units. To do that, again, there are a lot of methods which could be used, and we can use both spatial distributed methods and temporal distributed methods. We can use history. We can use comparison between models coming from different units, and actually that's what we tried. And again, we tried it on. We developed some kind of reputation and trust calculus, which allows us to evaluate the trust of the model coming from a particular unit, and then use it to make a decision to exclude it and to include it. And this is an example we tried on the data which were provided by NIST last year. That's the data coming from different banks, and some of the transactions were fraud transactions, and we tried again to find and exclude those fraud transactions in federated learning process. And it looks like we were able to improve the performance of conventional federated learning technique by excluding sources which provided fraud transactions. So we believe that we've developed some kind of a novel approach based on integration of knowledge coming from different areas, different cyber infrastructure parts, and different experts in various fields. And we considered interrelationship between those different parts and the knowledge which is coming from them. And we developed some kind of reactive and proactive and link methods to ensure machine learning application performance, or at least to try to improve it. And again, we tried some new techniques and to improve them in learning process too. And here are some products which we made available. I mentioned some data collections. That's the knowledge based about sensors, electronic sensors embedded into mobile devices, and another one which included security evaluation of different phones coming from various users. And we have developed a few apps which we made available on Google Play. Thank you very much.